Hi class, welcome to Module 5. So in Module 5 we'll talk about the concepts of correlation and regression. So let's get started. What is a linear correlation coefficient? Well, the linear correlation coefficient for paired data is represented by the variable lowercase r. It is a number that measures how well paired sample data fit a straight line pattern when graphed. Using paired sample data, we find the value of correlation coefficient r, usually using Excel. Then we use that value to conclude that there is or is not a linear correlation between the two variables. We will discuss methods of hypothesis testing for correlation. A correlation exists between two data sets when the values of one are associated with the values of the other in some way. A linear correlation exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. Look at these particular slides. So in slide A, the scatter plot of points exhibits a positive linear correlation with correlation coefficient 0.851. In slide B, the scatter plot exhibits a negative correlation between the data points pairs, and its correlation coefficient is negative 0.965. In slide C, there is no way to draw a line that represents the scatter plot of data, so these points are not correlated and thus have a correlation coefficient of 0. In slide D, the scatter plot of points exhibits a parabolic or quadratic relationship, and so there's no linear relationship between the points, and so the correlation coefficient here is very close to 0, namely negative 0.087. So what are the properties of correlation? Okay, next page. The sample of paired XY data is a simple random sample of quantitative data, where X is horizontal, Y is vertical. Visual examination of the scatter plot must confirm that the points approximate a straight line pattern. The outliers must be removed if they are known to be errors. The effects of any other outliers should be considered by calculating R with and without the outliers included. Okay, so some of the variables associated with computing the correlation between XY pairs. You have the number of pairs of sample data, the summation of all x values, the summation of the squares of the x values, and the square of the sum of the x values, and so forth. I'll explain these momentarily. So R is the linear correlation coefficient for sample data, and the Greek letter rho is the linear correlation coefficient for a population of paired data. The linear correlation coefficient R measures the strength of a linear relationship between the paired values in a sample. All right, so let me explore a few things here about correlation. First of all, correlation R always falls in this range, and it's a measure of the strength of the linearity between XY pairs. All right, so a review of what this symbol means. All right, so if I have something like this, what this means is that I iterate from 1 to 5, and I plug it into the subscript index, and I sum the ensuing values. So this basically means you sum 5 values. Okay. Now, when I have something like this, this means that I sum the squares of 5 values. Okay, x1 squared plus x2 squared plus x3 squared plus x4 squared plus x5 squared. Okay, now be careful when I have something like this. Oops, I don't need a parenthetical mark there. This means I sum the values and take the square of the sum. So this would be x1 plus x2 plus x3 plus x4 plus x5. I sum the values, and then once I get the sum, then I square it. Okay, so brief review of summation notation. All right. The linear correlation coefficient R measures the strength of a linear relationship between the paired values in a sample. Okay, and in Excel we use the correl function to find the correlation. So this is the formula for the correlation coefficient between XY pairs. And of course, you can use these, but you would probably want to use the Excel correlation function. All right, so the linear correlation coefficient, again, is the strength of the linear relationship. So properties of the linear correlation coefficient. Like I said, it ranges between -1 and 1 inclusive. If all values of either variable are converted to a different scale, the value of R does not change. So for instance, if we're measuring the relationship between shoe size and height, and shoe size and height are initially measured in centimeters, but we then change it to inches, the correlation coefficient would not change if you change the units from centimeters to inches. So it's insensitive to dimension change, or that is unit changes. The value of R is not affected by the choice of X and Y. So we can interchange the X and Y values and still get the same correlation coefficient. So I'll show you that in Excel momentarily. R measures the strength of a linear relationship, and R is sensitive to outliers, which can dramatically affect the value of R. Okay, and we'll see that in some of the worked examples. So first example. All right, so in this case we have shoe size and height, and we want to know if height is a function of shoe size. That is, if height is a linear function of shoe size. But before we do that, we want to analyze the correlation between shoe size and height and determine if there is a linear correlation. So we can use Excel to do that. So let's have shoe size, and this is in centimeters, and then height. Now, if we change the shoe size and height measurements to inches, the correlation coefficient would not be affected. So our data are, I'll plug in the data, 29.7, 29.7, 31.4, 31.8, and 27.6. The height is 175.3, 177.8, 185.4, 175.3, 172.7. Okay, so to calculate the correlation between shoe size and height, we use the Excel correl function, and we can do this, plug in the first range and the second range, and we get 5.9. Okay, now it doesn't matter, so it's insensitive to the order of which array you plug in first. Okay, so we can plug in the Y values first and then the X values, and we should get the same result. So it doesn't matter which order you put it in. So now the question is this a linear correlation relationship? So we want to test, so to do that, we want to test at an alpha of 95%. So alpha equals to 0.05, confidence level of 95%. All right, to do that, we need table A6 from your text. And this is it, table A6 from your text. All right, so the way the test for linearity goes, based on correlation, is the way you do it is you draw a number line from -1 to 1. Okay, this is the range of correlation values. Then you find your critical value based on alpha and the number of sample pairs you have. Okay, you find that. So in our case, we have 5 sample pairs, and alpha is 0.05. All right, so we find the critical value from that table. And so with n equals 5, alpha equals 0.05, the critical value is 878. All right, so this would be -878 and 878. Then we plot on this number line our test correlation value, which was 591. And so 591 occurs about here. Okay, so the interpretation is if your test correlation value falls in these regions, then you have significant linear correlation. If it falls in this region, okay, then you do not have significant linear correlation. So for this problem, we can conclude that the data are not linearly related at a 95% confidence level. Okay, so now, so what we do then is we square the R value, okay? So 591 squared is 0.349. All right, and so we conclude that about 34.9% of the variation in height can be explained by the linear relationship between lengths of shoe prints and heights. So only 34.9% of the explanation of height as a function of shoe size is there. So this is a weakly correlated relationship. Weakly correlated. So what do we mean by weakly correlated? It goes like this. The standard is this. If your test correlation falls here or here, if your test correlation value falls here or here, then you have a strongly correlated value. If it falls here in this interval or in this interval, then you have a moderately correlated value. So in this case, our correlation is moderately correlated, but it doesn't exhibit sufficient linearity at the 95% confidence level. And then if your correlation value falls here, then you have a weakly correlated or no correlation presence. Okay, that insofar as linearity goes. Okay, all right. Okay, so we concluded that there is not, at the 95% confidence level, there is insufficient evidence for a linear relationship. Okay, so no linear correlation at the 95% level. So let's see, can we work some problems? Yes. Okay, so given the linear, right here, so given the linear correlation coefficient R and the sample size n, determine the critical values of R and use your finding to state whether or not the given R represents a significant linear correlation. So alpha is 0.5, n is 25. Okay, so use the table A6. Okay, alpha 0.5, n is what, 25. And so the critical R value is plus or minus 0.396. All right, so then we go and what we do is we write down our number line. Okay, 0. So we minus 0.396 is here, plus 396 is here, and the test correlation was what? 543, which is here. Okay, so this is in the reject region. So in a linearity test, it goes like this. The population correlation is 0. So there's no linear correlation in the population, which is Greek letter rho. And the alternate hypothesis is population correlation is linear correlated. So this always results in a two-tailed test because of the presence of the not equal sign. All right, so based on the test correlation value of 547, there is significant evidence to demonstrate that the data are linear correlated within a 95% confidence interval based on the critical values of the test, based on the critical values of the correlation values from the table A6. So from table A6 you get your critical correlation values. Then you have your test correlation value, and it falls within the range of the reject null hypothesis. So you reject the null. Okay, or if it fell here, you would reject the null. Okay, which says that there's no correlation. If it fell here, then you would fail to reject the null and say that there is no correlation. Here there is linear correlation, no linear correlation on this interval. No linear correlation here, linear correlation here, linear correlation here. So that's how you answer that question. All right, so let's move on to the next question. The paired data consist of temperatures of randomly chosen days and the amount of certain kind of plant grew in millimeters. Okay, so we have this. So we want to find the linear correlation coefficient R. Okay, so again, what we can do is we can go into Excel, plug in the data, so we have what? Temp and growth. So temperature is 62, 76, 50, 51, 71, 46, 51, 44, and 79. Growth is what? 36, 39, 50, 13, 33, 33, 17, 6, and 16. So we want to know the correlation between temperature and growth, so we use the Corral function. Okay, select your first array. Okay, then your second array, close parentheses, and it's 0.196, thereabouts. Okay, so that's the linear correlation coefficient. Note the emphasis on the word linear. All right, so what are some common misapplications of correlation, linear correlation? Okay, linear correlation does not indicate causation. All right, just because we have a linear correlation coefficient doesn't mean that we can use it as a means of predicting values. So if we have a positive linear correlation between x and y, and if x increases, it doesn't necessarily mean that y will increase, okay? And vice versa. If x decreases, it doesn't necessarily mean that y will decrease. So don't mistake the correlation coefficient, the linear correlation coefficient, as a means of causality. It just means that there's a significant or non-significant linear relationship between the data pairs. Okay, if either of your x or y data points values is an average, then that inflates the value of correlation. So don't use average data when computing correlation. And of course, there may be some relationship between x and y even though there is no linear correlation. So what this means is, even though you have a statistically significant linear correlation coefficient between the paired data, doesn't necessarily mean that the data can be modeled by a linear equation. There could be an xy term or a quadratic term in the model for the data. So linearity is not necessarily implied in the data sets. All correlation says is that there is a significance of linearity between the data. It doesn't necessarily mean that the data are linearly related. Okay, so like I said before, when you analyze correlation, okay, you formulate a null and alternate hypotheses, where the null hypothesis is that there's no linear correlation in the population, and the variable used for the population correlation is the Greek letter rho. This isn't p, this is Greek letter rho. And the alternate hypothesis is that there is linear correlation in the population, and so since we use a not equal sign, this will always result in a two-tailed test. Okay, so the test statistic for linear correlation again is found in table A6, and we can also use the p-value method right here, the p-value method for a hypothesis test. So to use the p-value method to analyze the hypothesis, so for this problem, we assume that there is a linear correlation between, in the shoe size problem, we assume that there is a linear correlation between shoe size and height. And so we found the critical value, we can find the critical value, which at the alpha equals 0.5 was 878, and we concluded that there was no linear correlation. Okay, so now Another thing we can do is we can use the regression function in the data analysis tab, okay, which is here. Okay, so when you select regression right here, okay, and then you plug in your y range, which is height. Height is a function of shoe size, okay, and you run the regression, you get these outputs. And so the p-value for this is right here. This is your p-value. So the p-value is 0.294. All right. So how do we interpret the 0.294? Okay, the p-value of 0.294 is greater than the significance level of 0.05, and we fail to reject the null hypothesis. We conclude that there is not sufficient evidence to support the claim of linear correlation between shoe print length and height. So one thing I skipped over in the regression is that the regression by default has an alpha of 0.95 right here. There's your alpha. So by default, and you can set this to another alpha value if you wish. Okay, so just in case you want to know what the alpha is for the p-value test, that's how you validate it. All right. Okay. So now we go on to curve fitting, or regression analysis. We find the equation of a straight line that best fits the paired sample data. The equation algebraically describes the relationship between the two variables. So what we're going to be doing is we have our xy data, and we're going to be fitting a straight line through the xy data. So we have y is equal to mx plus b. Okay, and so what the regression equation will give you are these two values right here, the slope of the line and the intercept of the line. And you're given these, okay? And so you're going to find an estimate for the true equation, which we call y hat. Okay, this will be your estimated values. All right, so that's what we're going to be doing. Given a collection of paired sample data, the regression line is the straight line that best fits the scatter plot of data. It uses the principle of least squares and produces a line so that the squared sum of all the differences between the actual values and the values on the line are minimized. Okay, the reason we use this difference is that if we didn't sum all of the actual differences, would add up to 0, since some are above and some are below the line. So what the least squares does, okay, is this. I'll show you. All right, suppose we have our regression line. Okay, and our actual data are like this. Okay, we want to find the distance from this point to the line. Okay, and we call that D1. The distance from this point to the line, we call that D2. Okay, the distance from this point to the line, we'll call that D3. Okay, and the distance from this point to the line, we'll call D4. And the distance from this point to the line we call D5. All right, so we have all these distances. So the circled dots are the actual data. Okay, actual data. Now, and this is your regression line. This is the estimate of the model line that fits the data. So what we do is we calculate this sum. Okay, and so forth. All right, so we want to, and we calculate this sum for all potential types of regression lines. So this could be a potential regression line, that could be a line, that could be a line, and so forth. So you have an infinite number of possibilities of regression lines. And for each regression line, we calculate this sum. Okay, and we select the regression line, the one regression line for which this sum is the least. Okay, so that's what the least squares error analysis does. There's a way of finding it using a method from calculus, which is what Excel does, but I will not go into the math of that. Okay, so here's a problem. Use the given data to find the equation of the regression line. All right, so we want to find the regression line, so we can go into Excel. All right, so let's plug in our XY data. Okay, so x is 6, 8, 6, 8, 20, 28, 36. Y is 2, 4, 13, 20, and 30. All right, and so we can use the data analysis regression. Okay, and so our y values are here, our x values are here. Okay, and so our regression equation is found by looking at these two coefficients. So for this particular problem, you would write y hat is equal to 0.897 minus, no, check that, 0.897x minus the intercept, which is 3.79. So that's your regression equation using the regression tool. Alternatively, we can, let's see, 6, 8, 20. Okay, so this is our data. We can use a scatter plot. So if you go to Insert and then select the scatter plot chart, okay, here's the scatter plot of the data. All right, and then you can right-click on a point, and then you can add a trend line. And so the trend line is here, and then if you go to trend line options, then you can display the equation on the chart, and there's the equation on the chart. So that's another alternative approach. Okay, all right, what's next? So formulas for the slope and y-intercept of your regression line are given. Okay, the slope is the correlation coefficient times the standard deviation of the y values divided by the standard deviation of the x values, if you want to check that. Then the y-intercept is the average of the y values minus b1 times the average of the x values. So that's one way. And so, so here, this equation, use Excel. All right, so what are they? They're doing the shoe size problem. Here's the data set, and they want to find the regression equation for the shoe size problem. Even though it's not linear correlated, you can still find an approximating line. So do I still have my shoe size data? Yes, here it is. So if I wanted to find the regression equation, which won't be a good equation, we can do a scatter plot. Okay, and you can tell by the scatter plot that that's not a linear relationship. Okay, so right-click on a point, insert, add trend line. Okay, and then the approximate equation would be here. Okay, all right. Okay, all right, so let's do some examples. So the paired data below consists of test scores and hours of preparation for 5 randomly selected students. Use this data set to answer the questions below. All right, so for question 1, well, first of all, let me plug in the data. So go to another sheet. So I have x, y. Okay, so my x values are 5, 2, 9, 5, 2, 9, 6, and 10. And my y values are, what, 64, 48, 72, 73, and 80. All right, so question 1 is find the correlation coefficient regression equation and scatter plot. Okay, so select your data. Okay, go to Insert, go to Scatter Plot, select this, right-click on a point, add trend line. So there's your scatter plot plus trend line. To get the linear equation, regression equation, the linear regression equation display on the chart, here's your linear regression equation. And we want the correlation coefficient. Okay, so the correlation coefficient would be Correl, okay, your x range and then your y range. Okay, so your correlation coefficient is that. Okay, all right, so question 2 is, based on the linear correlation coefficient R, is this a good model? All right, so n is 5, alpha is 0.5, and so when we look in table A6, the critical value is 878. All right, so what you'll do is you'll go to you'll draw your number line. Okay, draw your correlation number line. Okay, and the critical values are plus or minus 878. So here's 8 minus 878, 878. Okay, and your test correlation coefficient is 924, which is here. Okay, so now, what are your hypotheses? Again, the null hypothesis is that the population correlation is 0. There's no correlation. The alternate hypothesis is that there is linear correlation between the paired sample data. And so since our test correlation value falls in the range of reject the null. So there is sufficient sample evidence to suggest that there is linear correlation in the test scores in the preparation, okay, based on this. So that's a 9 right there. All right. So the equation is a good fit. It's a good model. Okay, so let's go to Q3. Using the results from Q2, what is the best predicted test score for a student who spent 7 hours? So if this model is good, then you can plug in 7 into your regression equation and get an estimated score for a student who spent 7 hours studying. If this equation is not good, okay, in other words, if your test correlation value fell here in this interval or in this interval, then you cannot use this equation. You will not be able to plug in 7. What you have to do then is, if this equation were not good, is the average test score would be the average of the y values. Okay, so you would average this. It would be this. So you would report 67.4 rather than 69.5 as the average test score. You would use the average of the y values. Okay. Use the regression line for predictions only if the data do not go much beyond the scope of the available sample data. Predicting too far beyond the scope of the available sample data is called extrapolation and could result in bad predictions. Okay. If the regression equation does not appear to be useful for making predictions, the best predicted value of the dependent variable y is the sample mean. Y hat is the y value from the regression equation if the regression equation is not a good model. Okay. Then the best predicted value of y hat is simply the mean of the y values. Okay, so this applies to linear patterns. All right, so for instance, 10 pairs of data yield a very poor linear correlation coefficient of 0.003 for this regression equation. And the average y values is 5. What is the best predicted value of y for x equals 2? Okay, so since this equation does not have a strong linear correlation coefficient, you cannot take 2 and plug it into the equation and get 8 as your predicted value for y. No, you have to use the average y value of 5. So the answer is 5. Okay, so let's analyze prediction intervals. Okay, so what this means is when you use your regression equation. Your regression equation is this. Okay? All right, and so you want to know when you have for a given value of x, right? You plug in a given value of x and you get a predicted value, assuming that r is okay. So recall that when you calculate a regression equation using Excel, the alpha is 0.5. So what this means is that your predicted value, which is y bar, will be between some low value and some high value. Okay, so your predicted value is actually a value within a select range based on this alpha. Okay, and what you want to do is you want to find these two endpoints for your predicted value. So you can say, well, my predicted value is going to be greater than this number and less than this number. Okay, and so we'll go over the method for finding these two endpoints. What you'll do is you'll find a margin of error for y1, Okay, and you'll find a margin of error for the right endpoint. Okay, so you'll find a margin of error, and then you'll get y1, and then you'll use that margin of error to get y1 and y2. So it's your predicted value minus the margin of error for y1, predicted value plus the margin of error for y2, and so that would be the predicted value for y at a given x. Okay. Okay. All right. So to do that, you need to find a couple of quantities. First of all, you need to find what's called the standard error of the estimate, which formula is here, and then you need to calculate the margin of errors here. So you get this SE value from the STEYX method of Excel by plugging in the y values, y and x values. I'll show you in a second. And then you get your t statistic for a two-tailed test. And so for the t statistic, all right, okay, so the degrees of freedom will be n minus 2. The reason why we subtract 2 is because we now have xy pairs. And that will be your degrees of freedom, and then you'll use your alpha, and then you'll use your t-table and so forth. Okay, so let's see here. Let's work some examples. Find the standard error for the problem in Q3. Okay, so in Q3, that was the test score preparation problem, right? So let's go back to our Excel. So this is the Q3 data, okay, and we want to find the standard error of the estimate. So that is STEYX, okay, and then it says the known y's, which are here, okay, and then the known x's, which are here, okay, and so the standard error of the estimate is 5.4. Okay. Okay, and then it says the next question is find the 99% prediction interval for the test score of a person who spent 7 hours. Okay, preparing. Okay, and so we use E is here. Okay, so now note that the prediction for 7, what you do is you take 7 and you substitute it into your equation, which I think we did previously, right? Did we not? Yeah, right here. So 7, when substituted into the regression equation, gives a y hat of 69.513. Okay, so, and then your margin of error, okay, is given here is 34.677. So the y1 value is here, and the y2 value is here. So this is the range of values, range of test score values for a student who spent 7 hours preparing. So if the student studies 7 hours, we have a 99% confidence that he will score between 35 and 104. This is a fairly large range of possible values. One factor is the sample size. The actual score could vary substantially from the predicted score of 69.5. All right. Okay, so now we talk about properties of predicted values. We have things that are called total deviation, explained deviation, and unexplained deviation. Okay, so given in this chart, this graph, are properties of regression equations and predictions, and we have these definitions. The deviation for a value is y minus y bar, okay? And the explained deviation is y hat minus y bar. The unexplained deviation is y minus y bar. So y is your a y value from your data, your sample data, and then y hat is your predicted value for a given x. Okay. And then we have what's called total variation, which is the sum of the squares of the deviation. The explained variation, which is the sum of the squares of the explained deviations. And then we have the unexplained deviation, which is the sum of the squares of the unexplained deviation. So study this graph, which gives you a graphical representation of these definitions. All right, so if there is sufficient evidence of linear correlation, we can work with these parameters. For this worked example, y is equal to y hat. The regression equation is y hat is equal to 3 plus 2x. And one of the pairs of sample data is 5 and 19. So 5 and 19 is sample data, which is here, plotted here. And the 0.513, of course, is on the regression line. So the total deviation for these 3 points, okay, so consider these 3 points. We have 513 on the regression line, 519 sample data, and we want to find the total deviation from the average. So the average of the y values, okay, for the sample data, okay, the sample average was 9 for y, okay? And so the total deviation, okay, so for the x coordinate of 5, 9, okay, the total deviation is y minus y bar, which is 10. The explained deviation is y hat, okay, that's the predicted value on the regression line, 13 minus y bar was 13 minus 9 is 4, and then the unexplained deviation, which is the y value, which was 19, y being 19, minus y hat, which is 13, it's 6, okay, which is 6. Okay, so so you can use these to find these quantities. Total deviation from y bar equals 9, which is your sample average of the y values. Okay, so let's do an example. Now, some of these quantities can be calculated using Excel, and I'll show you. The equation of a regression line for the paired data below is this. Find the explained variation. Okay, so we have some data. All right, so let's go into Excel. Here's the data. All right. So we have what, XY pairs. All right, so 9, 7, 2, 3, 4, 22, and 17. These are X data values. Our Y values are 43, 35, 16, 21, 23, 102, and 81. All right, so we want to find what? The explained variation. To do that in Excel, we use the regression tool. So go to data analysis, go to regression. Okay, the Y values are here. The X values are here. So at the 95% confidence level, okay, the explained variation is here. It's this value right here for the regression. So it's 6531. This value, the residual value, is the unexplained variation, and this is the total variation for this problem. Okay, all right. So another example from the Word document. The equation of the regression line of the paired data below is y equals x3. Find the explained variation. So we want to, the unexplained. So we want to find unexplained variation here. Okay, so let's plug in our xy data. So our x data are 2, 4, 5, 6, 2, 4, 5, 6, and 7. Y data are 7, 11, 13, and 20. So again, we use the data analysis regression. Okay, our range is here. Our inputs are here. Okay, calculate. And so the unexplained variation is the residual quantity, which is 10. Okay. All right. So let's go back to our test score problem. Where was it? This was our test. Is this our? Okay. All right. So for our test score problem, we wish to find the unexplained variation. Okay. So the unexplained variation, again, we can run the data analysis Excel regression tool. And so the Y range is here. The X values are here. Okay. The regression here, and so the unexplained variation is this value right here, 87.4745. Okay. Now you can, of course, calculate the sum of the squares of y hat minus y bar. So to do that, let's see if we can do that. If I can find my data. Where's my data? Sheet 5. Okay, so I don't know. It consumes my data somehow. Shoe size, sheet 10, sheet 6. Is this it? Okay, here's our data. Okay, so let me get rid of this. Let me get rid of this. Get rid of this. Get rid of this. Okay, get rid of all this. All right, so here's our score data based on hours of preparation. Okay, so what we can do is all right, so let's bring back our scatter plot equation. So we know that, let's do this. We can go x, y, y hat, and then we have y hat minus y bar. Okay. All right, so let's build this table. So our 5, 2, 5, 2, 9, 9, 6, and 10. Okay, and then we have 80, 73, 72, 48, and 64. Okay, so what is y hat? So our regression equation was the regression equation was y hat equals to 3.524 x plus 44.845. Okay, so that was found previously. So now if we go back to Excel, we need y bar, right? So y bar is the average of the y values. So it would equal to average of this. Okay, so there's your y bar value, 67.4. Okay, so y hat, this will equal to 3.524 times your x value, which is 5, okay, plus 44.845. Okay, so 62.465 is your y bar, and so your y hat minus y bar is equal to this value minus y bar, okay? And so negative 4.935. Okay, so now if you want to calculate the y hat values, I think if you just grab this cell handle, if it'll let me, like that, and so there are your y hat values, and if you want to calculate this difference, okay, all right, that, okay, and so those are your, oops, that's not right. No, it's not doing that, okay. So this will equal to y hat minus y bar, okay, and this will equal to y hat minus y bar. This will equal to y hat minus y bar, okay, and then this will equal to y hat minus y bar. Okay, so what we need to do then is we need to square these values. Okay, so this is equal to squared. Okay, so we have that number. No, wait, y hat minus y bar. Yep. Okay, and then we need to square this value. Okay, and then we need to square this value. Okay, and then we need to square this value. And then we need to square this value. Okay, so This would be the square of y hat minus y bar, and then the unexplained variation will be the sum of these squares. Okay, so this would equal to, the unexplained variation is sum of these, okay, which is 511.643. Okay, actually that is the explained variation. Check that, that's the explained variation. All right, to find the unexplained variation, what do we do? The unexplained variation would be y hat, y minus y bar squared. Okay, so what we need is we need a y minus y bar. Okay, so we need those values. So this would equal to y minus y bar. Okay, so we have, wait a minute, oops, that doesn't look right. Y, so this would equal to y minus (64) let's see, y bar is 67, right? Let me check. Y minus, yeah, okay. So y minus y bar, which is here, okay. All right, so that's y minus y bar. And so let's see, can we drag? Can we get these values? No, we cannot. Okay, Control Z, it's not doing it properly. Okay, so we have y. Okay, so this is equal to y minus y bar. Something is strange. That looks a bit high, doesn't it? No, y minus y bar. I think this should be y hat minus y bar. So let's change this to, let's see. Let me check. Let's check the formula. So we are chasing the unexplained variation. So the unexplained variation is, oh, it's y minus y hat. I'm sorry. So y minus y hat. Okay, so the notes lopped off the hat part. That's why. Okay, so y minus, no, it would be y minus y hat. Okay, that's better right now. I should be able to grab this cell and drag it. Okay, yes, so they're your y minus y hat values. Okay, and so we need to square these. Okay. Okay, so y minus y hat squared. Okay, and so this would equal to this quantity squared. Okay, can we drag it? Okay, and we do. Okay, so does that look reasonable? That looks reasonable. And then to get the unexplained variation, we just sum up these values. So this would equal to sum of these numbers. Okay, and so that's your unexplained variation, which was shown in the regression. And then the total variation, of course, is equal to the sum of these numbers. So your total variation would equal to sum of that number plus the sum of these numbers. Okay, and that's your total variation. All right, so the next thing we need to work on is what? Okay, we need to do an example of an interval estimate for a predicted value. Okay, so let's see if I have some data for that or a problem for that. Let's see, do I have a problem? Oh yeah, here we go. So let's work the next problem. Okay, so this should be, yeah, explain variation. Okay. And then we found the unexplained variation, and we found the total variation. There was one problem that I wanted to work on. Right here, this one. Okay, so the equation of the regression line for the paired data below is y equals 3x, and the standard error of the estimate is this. Find the 90% prediction interval for y. Okay, so to solve this problem, what we need is, okay, so we need to find this. We need to find an interval estimate for the range of for a predicted value at x equals 3, for the value at x equals 3. All right, so what we have is we have y equals 3x, okay, and we want to find the range of values for the output at x equals 3. So that's your x naught value, okay, x sub 0 value, and our confidence level is 90%, so alpha is equal to 0.1. Alpha over 2 is 0.05. Okay, and so the data for this problem, we have 4 pairs of data. Okay, so let me go ahead and wire that into Excel. So x and y. Okay, so our data are 2, 4, 5, 6 for x, 2, 4, 5, 6, and the y values are 7, 11, 13, 7, 11, 13, and 20. Okay, so we want to find a range of values for y at x equals 3 at the 90% confidence level. Okay, so to do that, we will need the margin of error formula. Okay, that big intimidating formula. So the margin of error is this, right? So the margin of error is equal to t alpha over 2 times the standard error of your estimate times the square root of 1 plus 1 over n plus, okay, times this gosh awful looking thing, n times x naught minus x bar quantity squared divided by n, okay, times the sum of the x values squared, sum of the squares minus the square of the sums, the square of the sum. Okay, so this is what we need to do to get our e value. Okay, and so we need y hat, right? So our y hat value, so our y hat, of course, is plugging an x naught into your regression equation. So y hat is 9. Okay, so n is 4. Now, the degrees of freedom would be n minus 2 because you have x, y paired data. So you have two variables, two variable, and you have a matched pair. So the degrees of freedom would be 2, and alpha is equal to 0.05. So you look that up in your t table, right? So t alpha over 2 is equal to 0.05. get that. So T alpha, so DF is 2, and we need 0.005, so our T statistic is 9.925. No, our alpha, I'm sorry, our alpha is 0.5, right? Alpha is 0.5, so it's 2.92. So our T statistic is 2.92. Okay, so I'll close that. So this would equal to 2.92. All right, so now we need to compute E, our margin of error. All right, so we can use Excel to compute the margin of error. Okay, so what we need is margin of error is equal to 2.92. That's your T 2.92 times, now the standard error was given, right? What was the standard error for this problem? 2.2361. 2.2361. Okay, now times, okay, the square root of a lot of stuff. So that would be 1 plus 1 over n. So n was 4. Oh, Control Z. 20. Try it again. Margin of error is equal to 2.92 times the standard error of the estimate, which was 2.2361. 2.2361 times, okay, the square root of 1, okay, plus 1 over n, okay, plus, okay, so this would be another fraction, so this would be 4. The numerator of the fraction would be 4 times, okay, so x naught was 3, and we need an x bar. So x bar is equal to the average. Okay, so x bar is equal to the 4 times 1/4 plus 4 times 1/4 plus. Okay, so this would be 4 times average of your x values, which is this, okay, okay, and we need to, well, that's not going to work. That's going to be a little bit too challenging. Let's do this. Let's calculate our intermediate sums first. So x bar is equal to average of these numbers. Okay, so this is our x bar, okay? And then our sum of x squared values, okay? All right, so our sum of, so we'll have x, let's see. So 2, 4, 5, and 6. Okay, so x squared. Okay, so this is equal to that value squared. Okay, so that's 4. Okay, so the sum of the x squared values is this sum of these numbers. Okay, so that's 81, and then the sum squared, okay, would be this value equals to sum okay, squared. Okay, that's 289. Okay, so 4 plus 16 plus 25. That doesn't look right. Okay, so the sum of the values is this. 289. So 289 is the sum of the square, the square of the sum. Okay, so now we can calculate our, so what is this? That's the average. That's the sum squared. Okay, the square of the sums. The sum of the squares. Okay, so that's the sum of the squares. Sum of squares. Okay, and this is the square of the sum. Okay, and then this is the average. All right, so now we can calculate our margin of error. So this would be 2.92 t statistic, 2.2361. 2.2361 is the standard error of the estimate times the square root of 1 plus 1 over 4 plus 1 over 4 plus, okay, now we have 4 times, okay, x naught, which is 3, minus x bar, which is, where's my x bar? Oh, jeez. What is going on here? Oh, x bar is 4.25. Okay. We need to square that. Okay, then we divide this by what? Okay, 4 times the sum of the squares, which is 81, okay, minus the square of the sum, which is 289. Okay, so we do that. Okay, all right, and so that should give us our margin of error, which is 7.8. Okay, so that's our margin of error. And so what is the question? At the 90% margin of error, so we want to know the prediction for x equals 3. Okay, so y bar, of course, no, y hat, of course, is 9. So the prediction would be, let's see, the prediction would be your y hat value minus 7.8, okay, to 9 plus 7.8. Okay, so that would be 1.2 less than y less than 16.8. So that's the range of output for a given input of 3 based on the sample and the regression equation. All right. Okay, so what next? All right, so the final topic is we analyze the coefficient of determination. Okay, so let's go back to our Word document. So we've done that. The coefficient of determination is the amount of variation in y that is explained by the regression line r squared is equal to explained variation over total variation. R squared is the proportion of variation in y that is explained by the linear relationship between x and y. Okay, so find the coefficient of determination given that the value of the linear correlation r is this. Okay, so all you do is you square this value to get the coefficient of determination. Okay, so the last example for this lecture is a regression equation is obtained for a collection of paired data. It's found that the total variation is this, the explained variation is this, and the unexplained variation is 2. Okay, so find the coefficient of determination. So the coefficient of determination would be the explained variation, 18.592, divided by the total variation. Okay, so that takes care of that. All right, and so we have another question. Okay, so when you do this, you'll get an r squared of 0.854, okay? And so you conclude that 85.4% of the total variation in test score can be hours of preparation, and the other 14.6 cannot be explained by the hours of preparation. Okay, so that would be Q9. So, all right, so when we go back to our test example, okay, our test score example, let's see here, if I still have it. So here's our test score problem. All right, so if we were to do a regression, so let's do a data analysis regression. Okay, and so our y range is this, and our x range is this. Okay. All right, so the r squared value here is 85.4. Okay, and so this is your coefficient of determination, this value right there. And it basically says that 85.4% of the total variation in test score can be hours of preparation, and the other 14.6 cannot be explained by hours of preparation. Okay. So the next question is, if the data point, okay, so let me show you in the Word document. Okay, so if we add 100, so a guy studies for 3 hours and gets 100, is added to the data set, how would this affect the results of the regression analysis? And is this data point an outlier, influential point, or both? Okay, so, all right, so let's see here. Now, an outlier point could or could not affect the linear correlation, okay? If it does adversely affect the linear correlation, in other words, if the outlier point drives the equation from being linear to nonlinear, then it is an influential point. Okay, so what we do then for this problem is, I can find the data. Okay, so this is the data. No, that's not the data. All right, so I lost my data. Bear with me. Sheet 2, sheet 9, sheet 11, 8. I should have tracked the data. Okay, so this is the data, right? Okay. So what we do is we go ahead and we add a 3 and 100. Okay, so remember sheet 6 is the data set. And we analyze the R² value when we add this point. So data analysis regression. I have to clear it. Cancel. All right. Data analysis regression. Y values are now this. Okay, the X values are now this. Okay, our regression is, and then look at your R², 0.03, okay? And so the R value then is equal to the linear correlation coefficient then is the square root, right, of equals to square root of that number. So 0.1923, okay? And so that means that there's no linear correlation anymore. And so when you add that outlier point, only 3.7% of the variation is explained by hours of preparation. 3.7. So you went from 85% to 3.7%. And so not only is that an outlier, okay, but it's an influential point because it blew up your linear regression. It's no longer a the data are no longer linear correlated. Okay, so that should get you through Module 5. I'm going to write some notes on how to address the discussion post topic for Module 5, so be on the lookout for that.